Hey guys, so today we're in section 6.1, exponential functions. We're going to be talking about what exponential functions are, their domain, their range, and going through graphing two exponential functions. One via plugging in points and the other via transformations that we've already learned with using other functions up to this point. So what is an exponential function? Well, the form of an exponential function is a times bx, where a, b are real numbers. Typically, when we work with them, you'll see them more as whole numbers, integers, right? So something like 4 times 3 to the x power, or 2 times 5 to the x power, or even sometimes without any number in front. So just like 3 to the x power. Now, that's not saying you can't have a weird number as the base of an exponent. For instance, like pi, you could have pi to the x power. This is also an exponential function. But typically, you're going to see stuff more like this. All right, so how do these differ from what we've seen before? Well, usually we're used to seeing x as the base of an exponent, right? So like x squared and x cubed, and you can see the number, right, is the power. Okay, and these, we've already talked about these, but these are in the class of polynomial functions. But with exponential functions, x, instead of being the base of the exponent, x is now the argument for the exponent. And so what that looks like is now the number and the x that we've known before from polynomials have essentially switched places. So before, the base used to be x and we had a number as a power, and now what we have is the base being a number and x being a power. And so what does this really change about the behavior? Well, it changes on how fast these things grow. So I'm going to create a little table here comparing x squared with 2x, so you can see the difference in growth between these functions. So let's say we have x squared, right? And so we have 2 to the x. And so what happens when we plug in x equals 1 for both of these guys? Well, x squared, 1 times 1, that's 1. All right. What is 2? So let me be more explicit about this. So give myself more space. So when x equals 1, we have replace the x with 1, 1 squared, okay, that's 1. When we plug 1 into the exponential function, remember x is the exponent here, 2 to the first, that's just 2. We plug in 2, 2 squared, that's going to give us 4. We plug in 2 here, 2 squared, that's also going to give us 4. We plug in 3, 3 squared, that's 9. Here we have 2 to the third power, that's going to give us 8. X equals 4. We're going to have 4 squared, that's equal to 16. 2 to the fourth, that's also equal to 16. X equals 5. We have 5 squared, 25. We have 2 to the fifth, that's going to give us 32. X equals 6. That's going to give us 36. 2 to the sixth, that's going to give us 64. And I'm going to skip a few numbers and let's say x to the 10th, or x equals 10. That's going to give us 10 squared, which is 100. And 2 to the 10th, well, since we know 2 to the 6th is 64, it's going to give us 64 times 16. And that is going to give us 64 times 16. It's going to give us 1024. And so you can see how at the beginning these numbers that we're getting out look pretty similar, but as the numbers start getting slightly larger and larger, you can see how much bigger the the exponential function is growing compared to the parabola, right? The x squared function. And so that's generally the behavior of exponential functions, is they start growing really, really quickly. Okay? So let's go through and evaluate an exponential function, which is in the form a times b to the x. And so let g of x be 2 times 3 to the x. And how do we evaluate this? Well, it's 2 times 3, and the x is 1, so we're going to replace that with 1. And 2 times 3 to the first is going to give us 6. Okay, what if we plug in 0? Is that valid? Well, 2 times 3 to the 0th power. And since PEMDAS tells us to do exponents first, 3 to the 0th power is 1, right? Any number to the 0th power is 1, and 1 times 2 is 2. Okay, can we plug in negative numbers? Well, 2 times 3 to the negative first power. Remember, what do negative exponents do? Well, they essentially flip the thing that's being raised to it. So this 3 to the negative first is the same as 1/3. So it'll look 2 times 1/3. And so this is 2/3. And what if we plug in a fraction? Well, 2 times 3 to the 1/2. And what do fractional powers do? Well, remember that they're the same as radicals. So 2 times the square root of 3, right? Where the top number of the fraction is the power of the exponent, and the bottom number here, the 2, that's the power of the root. And so 2 times square root 3, well, that's just 2 square root 3. We don't have a better way of writing it. So there doesn't really seem to be a limitation on what kind of numbers we can plug into exponential functions. So what does that tell us about the domain and range of exponential functions? Well, if you see in our example here, we plugged in a whole number, 0, a negative number, and a fraction, and we were still able to get valid values out, right? And that's because there is no invalid value that you can't plug in. So for the domain of exponential functions, the domain is going to be all real numbers, or written in interval notation, negative infinity to positive infinity. Because no matter what type of number you plug in, you're not going to end up with an indeterminate value, right? You're not dividing by 0. You're not taking the square root of a negative number. Any number you plug in is going to be valid. But what about the range? Well, if you look at the numbers we plugged in, take a look at the kind of numbers we got out. Well, we got 6, we got 2, we got 2/3, and we got 2 square root 3. And so you'll notice that all of these numbers are positive, regardless of what kind of number we plugged in. And so your intuition should kind of lead you to, well, maybe it's not possible to get negative numbers in here. And so, well, not only is that true, but not only are you not able to get negative numbers out, right, the range, you're also not able to get 0 out, because 2, right, we'll just kind of simplify this really quickly. If f of x is equal to 2 to the x power, no matter what power you plug in here, right, if you plug a negative number, you're going to get a fraction out, just like we did here. If you plug 0 in, well, you're going to get 1, like we did here, right? 3 to the 0 is 1. And so there's really not any other types of numbers to plug in. Like, we can plug in whole numbers, that's just going to make our value bigger. And if we plug in fractional powers, well, that's just going to give us radicals, but those aren't going to be negative. So the range of exponential functions is going to be, you can basically get any fractions, but you can't get 0, because even when we plug 0 as a power, we get 1 out. So the range is going to be 0 to positive infinity. Okay? So the domain of exponential functions, every exponential function is going to be all real numbers, and the range is typically going to be 0 to infinity. Okay? So now let's go through really quickly and graph an exponential function. And so since we haven't graphed any exponential functions before, we'll do it the old-fashioned way, where we kind of plug in a couple numbers. And obviously the numbers that you pick here can make your life more difficult or easier. And so I'm going to stick with the numbers that we typically use, -1, 0, and 1. And just for a few extra numbers, I'm going to plug in 2 and -2. So what happens when we plug in -1, where we get 2 to the negative first power? And a negative power, recall, just flips the base of the exponent, so it's just going to be 1/2. All right, 2 to the 0th power, that's going to just give us 1 because any number raised to the 0th power is 1. 2 to the first power, well, that's just the same as 2. 2 to the negative second power, well, recall that that's the same as 2 to the second power, right, which is 4, just flipped as a fraction. So instead of 4 over 1, you're going to get the reciprocal, which is 1 over 4. Okay, and so there are x and y values for our function. And so if we come here and try to graph our function, and it's going to be a little crude because my drawings typically are. When we have -1, we have 1/2. So I'm going to make this 1. So maybe somewhere like here. When we have 0, excuse me, that's -1, 1/2. When we have 0, we're going to have 1. So that's going to be here. When we have, actually, let me change the color of the point so we can see it a little more clearly. When we have 0, we have 1. When we have 1, we have 2. Let me just make another line here. When we have -2, we have -1/4, so a little less than 1/2, right? And when we have 2 as x, we're going to have 4 as y. And so you can kind of see it's kind of creating like this little water slide type of picture. And so I'll try to draw this as best as I can. It's going to take a couple attempts. And so this is what the exponential function is going to look like. And luckily for us, in the general form, this is what all exponential functions are going to look like. So whether the base is 2 or 3, this general shape, this water slide shape, is going to remain the same. Essentially, the only points that will change are going to be dependent on the base of the function, but the general shape is going to be the same. Just how when you graph like 2x squared, this is a parabola, and you graph just regular x squared, it has the same type of shape. Whether you have 2x or 3 to the x, they're both going to follow this sort of water slide type shape. Okay? And so, because we've already learned about transformation of functions, now we can use that knowledge to apply it to exponential functions, something we just learned about, right? Like, we literally just learned what the picture looks like, but because we know how to transform any function, we can apply the transformations here. And so recall that if something happens on the outside of the parentheses, like this 3 being multiplied and this 3 being subtracted, we think of it as affecting y. So our new y values are going to be 3 times the old y values we had minus 3, okay? And if something happens on the inside of the parentheses of a function, we think of it as affecting x, right? And so we have our old x equal to x plus 1, and what we want to do is solve for our new x. And so all we really have to do is subtract -1 to both sides, and we get the old x minus 1 is equal to our new x. And so we can replace that here. And maybe I should have chosen a different color, but I guess we'll just keep it green at this point. And so you can see our old y's are right here, right, from our original function, this 2 to the x. And our old x's here from the parent function are here. And so typically you don't need to use all 5 of these. I'm just going to use the first 3, and I recommend that you do the same. For the most part, exponential functions are defined by really only 2 points. So you don't even need the third one, but we'll just do it here just as being a little more thorough than we necessarily have to be. And so to figure out our x's for this function, all we have to do is take our old x's from the parent function, right, to p of x equals 2 to the x, and subtract them by 1. So we take this -1, we subtract it by 1, and we get -2. 0 minus 1 is -1, and 1 minus 1 is 0. And then for the y values, well, we take the 1/2, we multiply it by 3, so it's 3/2, and then we subtract 3. So we have 3 times 1/2 minus 3. This is going to give us 3/2 minus 3. We need common denominators to subtract fractions, so this is 3/2 minus 6/2, which is -3/2. So there's a point for us. And then if we plug in the second one, well, we have 1 here to plug in, so we do 3 times 1 minus 3, which is 3 minus 3, which is 0. So that's a nice point. And then we can plug in the 2, and so we have 3 times 2 minus 3, which is 6 minus 3, which is 3. And so if we wanted to graph our new function, our transformed version, right, of the parent function, well, we're going to need 1, 2, 3, and -1. Let me try that again. -1, -2, 1, 2, 1, 2, 3. And so do this one in magenta. -2, right? Applying this first point here, -2 comma -1 and 1/2. Point's going to be right here. -1 comma 0, that point's going to be right here. And 0 comma 3. So x is 0, y is 3. That's going to be this point. And if you noticed, before we talked about how exponential functions they can't attain negative values, right? And so what ends up happening is you have this horizontal asymptote, just like we did for rational functions, that just so happens to be on the x-axis. But because now this function is transformed, the original horizontal asymptote is at y equals 0, right, for this function. But for our transformed function, it's been moved down 3 units. So our horizontal asymptote here is going to be at -3 in this, right? And so this point, and this point are the 3 magenta points that we've plotted here after being transformed. And so because we know the general shape of these functions is always going to be a water slide, we can kind of replicate it here. And I missed that point completely, so let me try that again one more time. And probably not going to get any better from me. Fortunately, I'm not an artist. And so this becomes our transformed function. And so you can use this, the same idea that we used for transforming all our other functions, right? Like this -3 tells us to shift the picture down 3 units. This x plus 1, because we do the opposite, tells us to shift the image left 1 unit, right? And then this 3 is a vertical stretch. But personally, I like to use the table and the parent table so that I don't really have to think about all of that too much. I can just plug in points and see how x and y have changed. And since really all you need to keep in mind is the original picture, right? How does the original function look like? And since we're just moving and stretching it, it's pretty simple to draw a sketch of it. Now, hopefully your guys' sketches are a little better than mine, but for the most part, this is what I'm looking for. 3 points, the parent function table, the new function table, and then the transformations, right? So where does this point move? Where does -1, 1/2 move? Well, it moves to -2, -3/2. And if you can come up with 3 points for me for the parent function and for the transform function, that's basically what I've been looking for all semester, and it won't change here. Okay, well, I'll see you guys in the next video. Try to keep these videos short.